Hi guys! Welcome back to my YouTube channel. Again, my name is Rica Casabuena, and for today's vlog, we will be having a Digital Electronics 2 laboratory experiment, which will be focusing on 8-bit pulse width modulations. So for our objectives, we aim to understand the pulse width modulations, PWM operations, and as well as to apply PWM in brightness control of our LEDs. So again, we will be needing our equipment and components, mainly our PIC16F18875 IC, which is the long IC. Second is our 220 to 1000 ohm resistor, our LED, any color of your choice will be best, our breadboard, our connecting wires, our Picket 3 or Picket 4, and our power supply. So we just have to follow the procedures written in this paper to successfully perform our experiment. Let's go to our Mplab IDE. Now, before we proceed, providing an introduction, pulse width modulation is effective and commonly used as control technique to generate analog signals from a digital device like a microcontroller. Pulse width modulation, or PWM, helps in voltage regulation and thus finds its use in controlling brightness in smart lighting systems, or let's say for example our LED, and also controls the speed of motors. So in this experiment, we will be controlling our LED, specifically its brightness, using our Mplab IDE and IPE using our Picket 3 and our IC. So let's start. So now, using our Mplab X IDE, we will create a new project. Okay, a new project here. So it will be a microchip embedded standalone project, and then click next here. And then we will be using our PIC. Okay, let me just find it. PIC 16F18875 IC. Okay, and let's click next. So we will be selecting our compiler here, this one, and then let's name this Casabuena Experiments XP, then 7. And then let's select this one, and then let's click finish. So let's just wait for it to load up. So after loading up, we will be clicking MCC here, and let's just wait for the pop-up, which will allow us to save our code configurator. So let's just wait for it. Okay, so this one. So let's save my config.mc3 here. So we are already in our MCC. Let's wait for it. Let's select the right package for our IC. So in this part of our pin manager, we will be selecting PDIP for the right package of our IC. So here in the system module, we will be selecting or adding our PWM as well as this one. So let's add this one. We will be adding PWM. So we will be selecting PWM6. So let's add this one. Okay, as you can see here, it is already added. And then on our timer, we will be adding timer 2. So let's add this one. Okay, as you can see, it's already added. So under timer 2, we will be setting up our settings wherein our control mode will be rollover pulse. Our start reset option is software control, and then clock source should be changed from high frequency to frequency oscillator over 4. Okay, and then polarity should be right edge. Prescaler should be 1:1, and postscaler should be 1:16. Okay, take note of that. And then for our timer period, we will be selecting the maximum value, which is 16.384 milliseconds. Okay, let's just type it correctly, and then this will be all set up already. So after setting up the settings for our timer 2, we will be going to our PWM6, and we will be setting up its simulation settings. So we will be enabling PWM here, so it should be checked. So our select a timer should be timer 2, okay, and then our duty cycle should be 50% as is, and then our PWM polarity should be active high. So after this, we will be going to our pin manager grid view, and then we will be selecting the pin number or the port for our LED output. So based on the paper, we will be selecting our pin number 6. Okay, we will be selecting our pin number 6 or port A4 as the output for our LED. This one. Okay, as you can see, it should be the RA4 here should be our output for our LED. And after this one, we will go to our system module, and then let's make sure that the settings, the simulation setting is correct. So our simulation settings should be our oscillator select should be HF INTOSC, and then our HF internal clock should be 4 MHz, and then clock divider should be 4, and then our low voltage programming should be enabled. After this one, let's go to our interrupt. Yes, our pin module here. So make sure that our analog and WPU and WPU is unticked and IOC is selected, and none for IOC is selected. After this one, we will be generating our code. Okay, so let's just wait for a notification that our generation is complete. Okay, so as you can see, generation complete. We will now proceed to building our source code. So now, after generating our code, we will go to projects, and then we will already have our main.c file. Okay, as you can see here. Okay, this experiment number 7. So let's double click on this one, and then let's go to our source files, and then let's double click main.c file. So here we will be encoding our code later on, and then we will also open pwm6.c file here, and to encode our code, we will be finding for an option here, which is the pwm6 initialize, which will let us initialize or let the code acknowledge the pwm6 source code. So let's go to our main.c file here. So here we will be inserting our code. So let's paste pwm6 initialize here, and then let's write our code. So for our first code, we will be encoding a for command wherein we will be considering duty is equals to 1, and then we will be setting an interval for duty wherein if duty is less than 512, okay, the function or the program repeats unless the source code will repeat if the duty value is less than 512. Unless if it is not less than 512, the program will not repeat. So we will be using duty. So let's type here, okay, 512, and then we will be using duty, and then we will be using duty plus 10. So that's our source code for our first for loop. And then for our second for loop, let's use another bracket here, and then we will be using the pwm6 load duty value. So we can find it here, okay, we can find it here on our pwm6.c file. So let's copy this one, and then let's go back to our main.c file, and then let's paste it here, and then we will be typing our code. So we will be declaring duty here, and then for our next loop, let's type 4, and then int, and delay, and then we will be using 1 as the value of our delay, and then we will be using again a definite interval for our values. We're in we use 512. Okay, 512 here, but this time we will be using 500, and then we will be using the delay command, and then we will be typing delay plus here. So same logic with our first for statement. Okay, if the delay value is less than 500, the for command will repeat not unless the delay value is not any longer less than 500, or let's say it exceeds the 500 value. Okay, so this is our source code. So let's add another option here in another source code, which is a parenthesis and a semicolon inside. Okay, it's not a parenthesis, it's a semi bracket, okay, with a semicolon inside. So let's make sure that all of the brackets are correctly placed on our source code, and after this one we will be building our code. So let's click the hammer here, okay, and a build successful should pop up on our screen. So let's just wait for it. Oh, before you build your code, let's just first check if our code is correct. So that should be for int duty is equals to 1, and then semicolon, and then duty is less than 512, and then duty, okay, it should be duty is equals, okay, to duty plus 10. Okay, so make sure that it's correct already. We already declared the duty code here, and then our source code here, and then this one, and then delay plus. So let's build our code again. Okay, as you can see, build successful. We will now be connecting our PIC3 to our Mplab IPE. So now we will be programming our IC by connecting our PIC3 to our Mplab IPE. So we will be using a microchip adapter to make the connection easier, okay, because this will directly connect our PIC 16F18875 to our PIC3. So let's connect it here, okay. So just put our 40-pin IC here, and then this one, we will be pulling this down, okay, to lock our IC. So as you can see, our microchip adapter is connected to our PIC3 here, which is also connected to our Mplab IPE. So now, we will be programming our PIC3 and our IC. So just to explain, okay, the first pin of our microchip adapter is our MCLR, okay, MCLR pin, and then the next pin will be VCC, okay. or our VDD. The next pin will be ground or our VSS. Okay, as you can see here, it is labeled. And then our fourth pin is PGD and our fifth pin is PGC. Okay, so those pins will be connected here. So the yellow wire here is our MCLR, and you just have to connect the pins here correctly. So that will be easier compared to the previous methods that we are connecting our IC to our breadboard, and we are individually connecting the wires to our Pico 3. Okay, so that's the role or the use of our microchip adapter. Now we will be connecting our Pico 3 to our Mplab IPE. So let's connect this one. So our Pico 3 is already recognized by our Mplab IPE. So let's just wait for our Pico 3 to be connected. So as you can see on the screen, we will be having a portion. So we will be setting our, changing our advanced mode settings. Okay, as usual, our password is microchip. Okay, let's log in, and then our power will be 3.125. Our power target circuit from Pico 3 should be tick. And let's go to operate, and then let's select our hex file. Okay, let's select our hex file here. So it's the third year, and then third year, second sem, under digital lab 2, and then let's find our experiment number 7 here. So this default, and then production, and then our hex file. So let's load it, and then we will be clicking program to program our IC. So let's just click this OK, and then there will be a pop-up saying programming complete later on. So let's just wait for it. Okay, our program is completed, so we will now be constructing our circuit. So now we will be constructing our circuit. So for our circuit, we will be needing a breadboard, an LED, okay? Any color of your choice will be the best. So our PIC 16F18875, so let's remove it from our microchip adapter, and then let's connect it to our breadboard. So here. And we will be also needing our connecting wires. So let's just connect our IC. So in accordance to our pin configuration, we connected our LED as our output on RE4 or on the 6th pin of our IC. So let's first connect it. So let's count 1, 2, 3, 4, 5, 6. So this will be our output. So let's connect it here. Okay, and let's connect our LED here. Okay, and then the positive terminal of our LED should be connected here, and then the resistor, the 360 ohm resistor, should be connected to the negative terminal of our LED, and then let's connect the resistor to our ground. So let's find a gray wire here. Okay, let's connect it to the ground, and then let's connect our VDD or our VCC to the 5 volts battery supply. Okay, so it's on 11 pin, so 6, 7, 8, 9, 10, 11. Okay, this is on the positive terminal. Okay, positive terminal here, and then the 12 pin is VSS, which is the negative terminal, which is connected to the negative terminal of our 5 volt supply. And then do not forget the 32nd and the 31st pin. So 32nd pin or VDD is connected to our positive supply. Okay, so 40, 39, 38, 37. Okay, wait. 40, 39, 38, 37, 36, 35, 34, 33, 32. Okay, 32 is connected to the positive terminal as well, and 31st is connected to the ground. So let's find a black wire here. Okay, so 31st is connected to the ground. Okay, so for this circuit, we will be having this connection here. Okay, so this will be our circuit for our experiment number 7. So to test our circuit, we will be connecting a 9 volts battery with a connector here to connect this on our power module, which will be giving our circuit a 3 to 5 volts power supply. So this is our battery, and then this is our power module. So to test our circuit, we will be turning on our power module. So let's turn it on. Okay. As you can see, our LED is turning on slowly. Okay, not just turning on abruptly, but it is turning on slowly. So just like what we mentioned in our objectives a while ago, we aim to control the brightness of our LED using this experiment. So as you can see, the LED is slowly turning on with an initial brightness of just a dim light, okay? And as time passes by, the brightness of our LED is being maximized, okay? And as you can see, if you can be more technical, the light or the brightness of our LED conforms to our set value in our source code. So we will be modifying our code later on, which will allow the LED to light up with a delay that we will be setting on our source code. So let's modify our code. Now, we will be reprogramming our IC wherein our LED will adjust its brightness at a faster rate of time. So let's go back to our source file here, and then our main.c file. So let's load it. Let's just wait for it to load up, so it takes time. So since we already used +10 here for our duty, okay, since we want the LED to adjust its brightness faster, then we will be increasing this numerical value. So we will be considering duty plus, let's say, plus 60, let's say. So after this one, we will be building our code. Okay, let's wait for it to say that build successful. Okay, build successful. Let's go to our Mplab IPE here, and so we will be reprogramming our IC. So now we will be connecting our PIC3 and our IC to reprogram it, wherein our LED will be adjusting its brightness faster than the previous one. So let's just wait for it. Okay, so let's check our settings again. Okay, for it to work properly, so it's 3.125, and our power here will be ticked. So let's reconnect it again. Okay, so we will be needing to set up our settings here so that our program will be working fine. Microchip is the password. So power should be 3.125, and then the IDE should be ticked. So let's browse our program here. So the new hex file that we built a while ago, that will let the LED blink faster. Or in the end, that will let the LED to adjust its brightness faster. So let's program. Let's just click this OK. And let's wait for this pop-up saying programming complete. Okay, so now let's test our circuit. So now to test our circuit, wherein we modified our code for the LED to adjust its brightness faster than the previous one. So let's turn on our power module here. Okay, as you can see, our LED is adjusting its brightness faster, or it seems that it's blinking, but it's absolutely not. This happens because we increased our increment for the duty, which is we turn it, or we adjusted it to 60 from its previous value of 10. So this means that if you want to make the adjustment of the brightness lower, you just have to consider a value lower than 10 as your increment for duty. But if you want to increase the adjustment of the brightness, okay, if you want to increase the time, then you just have to increase the value of the increment for your duty cycle. So that's all for our experiment number 7. I hope you learned something from our experiment today, and I hope I will be seeing you on our next vlog.